equilibrium mass when the mass is not changing over time. And then at the end of the run, we wash it using the background buffer so that all the loosely attached molecules or which have not adsorbed can be washed off. So this is the irreversibly adsorbed mass. So this is the technique which I am going to use. And these are the results for the QCM results for lysozyme adsorption. So the red ones are the hydrophobic groups, the gray ones are the hydrophilic, and the black ones are gold. So this is the control and this is the TMAO adsorbed on gold and the difference in adsorption amounts. All these experiments have same concentration of lysozyme, that is 1 micromolar. So as you can see that there was gold, and when TMAO was physisorbed on gold, there was a reduction in lysozyme adsorption. But the slope of this mass versus time was changing, as you can see, and it is evident that if you leave it for sufficient amount of time, probably all the TMAO will be washed off from the surface, and so the TMAO layer is not supposed, it doesn't appear to be very stable on this surface. Whereas for hydrophobic SAM surface, like CH3 SAM and TMAO modified, there was a huge reduction of lysozyme. There was not much effect, there was not much advantage on the hydrophilic SAM, but hydrophilic SAMs are themselves good for, they are protein resistant, so we don't care much. So they have a marginal improvement. And the gold standard is PEG, which is the well-known protein resistant layer. And we can see that this modified layer is as good as PEG3 SAM, if not better.
What do you mean better? It's not better.
I mean, it can go below that. Yeah.
Close.
It's quite close, comparable.
Not better. Not from there.
So we tested the same phenomena using another method. This is the atomic force microscopy force measurement. So quickly I'll go over the technique. So this is a cantilever, and there is a sphere attached to it which is coated with gold. We coat it with gold so that we can have SAM chemistries over these, and we can functionalize it and tune the wettability of this probe. And so when this probe moves towards the surface, initially there was zero force, zero interaction energy. As soon as it hits the surface, it experiences repulsion from the surface because you go press it or trigger it against the surface. So you see this repulsion. And then we start taking it off away from the surface, above the surface. So the surface and the interaction between these groups hold the sphere for some time. So this is the attractive curve. And at some point of time, when your trigger in the upward direction is strong enough, it just pops up. So this jump is the measure of adhesion energy. So this is how the technique works. And this is the schematic. So we have used the same 7 chemistries which I have shown you earlier in the QCM experiments. They are by the same color code. And so protein molecules were on the surface and the chemistry were on the top. And we went on at different points on the surface and collected like 100 force curves for each surface, and then made a histogram and fitted in Gaussian to calculate the force. And these are the results for that. So for gold and TMAO adsorbed gold, there was not much difference after washing. So that means the TMAO was not present, or the effect was not felt. But there was a massive reduction in adsorption for alkane thiol SAM, the hydrophobic SAM. And similarly, for not much effect was seen for hydrophilic SAM, and PEG SAM was the lowest.
So the lysozyme is immobilized on the AFM probe?
On the surface. Because we deliberately did not immobilize lysozyme on the surface, on the tip, because we don't want to use the same set of molecules
so
again
what's
and
on
again.
the tip?
It's these different chemistries.
So the chemistries are both the tip and below?
No.
No.
So this surface is just lysozyme.
Okay.
And we go to different points on the surface so that you hit the fresh lysozyme molecules every
What's
time.
on each surface? Just look at the picture on the left there, the one on the very left, the bottom.
Yeah, so the proteins are on the surface.
They are covalently.
Covalently attached to the surface. Thank you.
Yes,
That's
sorry.
all, that was my question.
They are covalently attached, yeah.
And then you vary the top
Got it.
surface.
So we used AFM, we used QCM, and then we thought that there is another very common way of checking the wettability. So if all the O's were pointing upwards, you should see a massive increase in wettability, or the reduction in contact, or the increase in contact time. So So these are the results for all the chemistries, but just focus on these two. So CH3 SAM has a very high contact angle. It's a very less wettable surface, hydrophobic surface. And when it was modified with TMAO, there was a decrease in contact angle, but it was not appreciable. It was not, if all the O's were pointing up, you would expect contact angle to become something like C1H2 SAM. So we were not able to interpret this result, that why are we are getting a low adsorption, we are getting low adhesion, why the contact angle is not so low, and what is happening. And I tried using XPS, I tried using other probes, but they had limitations. They cannot see such a small molecule and see the rotation of such a small molecule on the surface. So Professor Gadi's group, Sumant, who was a graduate student then, now a doctor. So he actually carried out calculations, and they also showed that using an interaction parameter. So just quickly I will go over it. So if it is negative, that means the TMAO is excluded from the surface, from the interface. But if it is positive, that means it is sticking to the interface. So from these results, you can see that from lysozyme surface, TMAO was excluded, as said by other, as has been pointed out by other scientists also, that it excluded itself out. Whereas it was sticking onto the CH3 SAM preferably, and it was stable. So all four, the contact angle AFM and the QCM experiment and the MD simulation proves that TMAO is actually quite stable on CH3 SAM. And looking at the surface, the blue is the excluded, so you can see that the red ones are the TMAO sitting on the protein surface. This is the lysozyme surface, whereas the blue is the exclusion. So it's preferably excluded. So this is the VMD picture, a direct results of the simulations, and the decrease in contact angle was not massive, because instead of O's being pointing upwards, TMAO was sitting in this fashion. It is 90 degrees from the vertical. So why does it sit like this instead of what we had assumed earlier? So Sumant actually carried out calculations, and so this is just a one snapshot of the results. So because the water layers at the hydrophobic surface, so water has maximum density at a certain height. Because of the geometry of this molecule, if it was sitting like this, which we had hypothesized earlier, it would just lose, due to the geometry, it will just lose all the hydrogen bonds with the water, because this is a hydrogen bonding group. To maximize the hydrogen bond, it can topple itself, it can rotate itself by 180 degrees, and it can have a maximum water density, but that in this case, it will lose all the hydrophobic contacts. So this is the optimal orientation in which it has optimum number of hydrophobic contacts, and it orients itself to the bottom. Besides this mechanism, it can also bury itself into the interstitial spaces on the CH3 SAM because they are of the comparable length scale. So that is why we think that this molecule was stable, and it was pointing this way. So now, having established that TMAO is stable on these hydrophobic SAMs, and we have massive reduction in adsorption of small molecules, we thought of testing the stability of this layer, and then interrogating it by putting bigger molecules, because since until now we have just tested lysozyme and TMAO. So to the first part, the temperature stability was calculated using the contact angle measurements. So this was the wettability of CH3 SAM over temperature. This is TMAO on CH3 SAM. And you see, when the temperature goes about 40 degrees, TMAO starts to lose from the surface, or we start losing it off. So the layer is, it's not very stable, but it's stable up to around 40 degrees centigrade. The time dependent stability was checked using QCM measurements. So TMAO was adsorbed on CH, so the surface of the QCM crystal was gold, was coated with CH3 SAM, and then we injected TMAO solution over it. The adsorption period was 10 hours, and then the washing period was 10 hours. So that means that all the loosely attached TMAO left after washing step, but for 10 hours there was appreciable, or the 50% of the TMAO was absorbing on the surface, which is an appreciable amount. So we can say that for at least 10 hours and for at least 40 degrees C, the layer was stable. So now in my kinetic talk, there was suggestion that we should be trying other bigger molecules and other osmolytes. So there was suggestion by Professor Karande and Professor Gade.